metal ring of mass m and radius r is placed on a smooth horizontal table and is set rotating about its own axis in such a way that each part of the ring moves with a speed v. Find the tension in the ring. So let us draw a ring arrangement. So we are considering a ring like this, and we are drawing the central line. So from the center, which is O, we are considering a small part ACB. So we are considering a small part which is A, C and B, such that the arc ACB is subtending a total angle of delta theta at the center. So which I can write as delta theta by 2 and delta theta by 2 from the center line as shown. So now we are considering something like this, that on being rotated, some tension will be generated in the ring. So at A we draw the tangential value of tension like this, and at B I draw the value of tension like this. Apart from the tensional force, the weight of the ring and the normal reaction force by the table is also acting on the ring while it is rotating on a smooth horizontal table. So the first thing that we do is we break the component of tension. So if we break the component of tension, so the tension is acting tangentially, that is making an angle of 90 degree. So I can say that this angle is also delta theta by 2. So this angle will become 90 minus delta theta by 2. So the component of tension in the inward direction is going to become T2 cos of 90 minus delta theta by 2, that is T sine of delta theta by 2 in the inward direction. Similarly, the component of tension at B will also be written as T sine of delta theta by 2. So now this value of the two tension is going to balance the radial component, that is delta m v square upon r, which will be directed away from the center of the ring. So if we write the equation, so we can write it as 2t sine delta theta by 2 must be equal to delta m v square upon r. So this is the expression which we can write from here. Now the next thing which we say is the mass of this segment ACB. So considering mass per unit length, I can write delta m, which is equal to m upon 2 pi r multiplied by the length of the segment, that is r delta theta. So the length of the segment is calculated as angle is equal to arc length upon radius. So we calculate the delta m, which is obtained as m delta theta upon 2 pi. So this is the value of the mass of the segment ACB. So if we put this value in the above equation, that is equation number 1, and this one is 2. So we will obtain something like this. So 2t sine of delta theta by 2, which can be written as m upon 2 pi delta theta v square upon r. Now for very small angles, we can say that sine theta can be approximately written as theta. So for very small angles, we can write sine theta approximately equal to theta. So over here, using this approximation, I am writing it as delta theta by 2, which is equal to m upon 2 pi delta theta v square upon r. So from here we can calculate the value of tension, which is equal to mv square upon 2 pi r. So the value of the tensional force in the ring is going to be mv square upon 2 pi r.